Okay, we're recording. All right. So let's take a look at pages 3 and 4 of the Chapter 7 Notes Part 1 handout. And number 3, well, actually, both of these pages are about graphing exponential functions. And really, they're going to follow kind of the same pattern that we've been doing for like the square root and the cube root functions and the parabolas and all that stuff, where you graph a parent and then you figure out how to stretch and shift it. And so this one, we're starting just with a really basic one, which would be a parent function. So 2 to the x. So anytime you have some base to the x, really you're pretty much always going to start with those 5 x values, -2, -1, 0, 1, 2. So let's fill in the table. If I have 2 to the -2, 2 to the -2. Remember, to get rid of that negative exponent, you can just flip the thing over to the bottom. This would be 1 over 2 squared, which is 1 over 4. So I'm going to put 1/4 right here. If I do 2 to the -1, that's going to be 1 over 2 to the first, so just 1/2. Anything to the 0, almost anything really, not 0 to the 0, but anything else to the 0 is going to be 1. 2 to the first is 2, and 2 squared is 4. So then I get a 2 here and a 4 here. Okay, so then part B says, what's the end behavior of the function? So end behavior, remember, that's what happens when x gets really, really big, what happens when x gets really, really small, those sorts of things. So let's take a look at what happens when x goes to -infinity. So as x goes to -infinity, well, that's kind of like saying what happens if you plugged in like a huge negative number into x. So if that happened, let's take like -10,000. So if we plugged in -10,000 for x, well, that's going to turn into 1 over 2 to the 10,000. Well, that's 1 over a huge number on the bottom. But 1 over some really big number is basically pretty close to 0. And no matter how big this gets, if I added a couple more zeros, well, then the bottom just becomes an even bigger number. So it gets even closer to 0. So really the y approaches 0. When x is huge, well, that's like plugging in 2 to the 10,000. Well, that's just a big number. So this thing just gets bigger and bigger and bigger. So it goes to infinity. You can kind of picture that by looking at the chart. You know, as x gets really big, you notice these numbers just keep doubling as I go up. So if I just keep doubling numbers, they eventually just keep getting bigger and bigger and bigger without any bound. And if I go backwards, you know, as x gets more and more negative, so that's going this way up the chart, well, the values keep getting cut in half as I go backwards. So I get 1/4 and 1/8 and 1/16 and 1/32. So it just keeps getting smaller and smaller and smaller, but it doesn't ever go negative. It just gets closer and closer to 0. Okay, so let's graph the function. All right, so I'll put it over here. Actually, let me move that over. So we don't get any negative values for y, so I'm just going to graph the top part here, x, y. And I've got, let's see, let's go about 1 there, 2 there, 3 there, 4 there, -1, -2, -3, -4. And we go up 4, I'll go up 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's plot our points. We've got -2, 1/4, which is pretty low. You know, it almost does it, like there. And then -1, 1/2 would be about here. 0, 1 is right on the axis there. 1, 2 would be about here. And 2, 4 would be about here. And you can kind of see, you know, if I did 3, well, 2 cubed would be 8. So that would be up here. And if I did -3, well, that would be 1/8, 1 over 2 cubed. So 1/8 would be even lower, like right there. So you can kind of picture what this thing looks like. You can sort of see this thing is growing exponentially. Just like that. Right? Okay, so there's our graph. Let's fill in a couple facts about it. Let's talk about the domain. Well, that's all real numbers, right? Because we can plug in any x that we want. The range, notice it's just above 0, so y is greater than 0. And we do have an asymptote here. Over on the left side, this graph gets really, really close to 0. So we say that on the left side of the graph, we have an asymptote of y equals 0. So yes, the graph has an asymptote on the left, y equals 0. Okay. So there we go. And that's going to be true for 2 to the x, 3 to the x, 4 to the x. Any number bigger than 1 to the x is going to just go up and to the right like that. And they're always going to have this domain and range and this asymptote. Okay, let's take a look at the next one. So when we graph cubic roots like this guy right here, we would graph the parent function first, that cubic root of x. I don't know if I crossed in the middle. The cubic root of x. Cubic root of x. And then we'd end up doubling it, all the y values. And then we'd shift 5 to the right and 3 up. So that it's going to work the same way with these exponential functions that have gotten a little more complicated looking. The key here is first figuring out what your parent function is. And up above we graphed y equals 2 to the x. So the parent function looks sort of like that. And in our problem, that's the 4 to the x right here. Okay? So the parent function is y equals 4 to the x. So let's make a chart for that, and we'll start with -2, -1, 0, 1, 2. Okay, well 4 to the -2 is the same thing as 1 over 4 squared. I don't know what's wrong with this pen. 4 squared underneath. So that's 1/16. And then 4 to the -1 is going to be 1 over 4. 4 to the 0 is going to be 1. 4 to the first is going to be 4. 4 squared is 16. Okay. So then to get to the next step, we would do any vertical stretches. And in this case, our vertical stretch is 3. It's that multiplier in front. So vertical stretch by 3, it's going to give us y equals 3 times 4, brutal, 4 to the x, just like that. So the x's stayed the same. Whoops, that's not 3. -2, -1, 0, 1, 2. And the y's all get multiplied by 3. So instead of 1/16, we've got 3/16. We've got 3/4. We've got 3, 12, and 48. And then we need to do our shifts. And notice that the x has a -1. That means 1 to the right. And then the whole thing has a +2, so that's 2 up. So I'm going to add 1 to my x's and add 2 to my y's. This marker is killing me. Let's try this again. Let's try this. +1 +2. All right, so +1 to the x's. That's going to raise everything by 1. Add 2 to the y's. Well, that'll be 2 and 3/16. 2 and 3/4. 5, 14, and 50. Okay. Now, before I graph the thing, let's do the parent asymptote. Just anything to the x by itself has an asymptote of y equals 0. right? Just like above, 2 to the x had, y equals 0, so 4 to the x has y equals 0. The domain, well, you can plug in any x you want. It's all real numbers. And the range, well, that's just all positives, right? So then think about it. If I stretch by 3, that means multiply the y's by 3. So the asymptote doesn't change because 0 times 3 is still 0. So it's still y equals 0. The domain, well, I'm not doing anything to the x's, so it's still all real numbers. And then the range, well, if I multiply y greater than 0 by 3, well, 0 times 3 is still 0. And then the moving up 2 means all the y values increase by 2. So now my new asymptote is y equals 2. And I'm adding 1 to all x values, but all x values plus 1 is still all x values. So it's still all real numbers. And then if I add 2 to the 0 for the y's, my new asymptote is now y is greater than 2 because I went up 2 units. So let's graph this thing. And I have to go as high as 50, so I'm going to go by tens here. Let's go 10, 20, 30, 40, 50. And let's see, I start at -1, and I go up to 3. So 1, 2, 3. Let's graph the asymptote first. So my asymptote is y equals -2. So that's going to be pretty low here, but just above the axis. So I'm going to draw in this. Whoop, right there. So that line, y equals -2, is my asymptote. And notice the range is everything above 2, so I should never actually go below that dotted line. So if I plot my points, I'll do it in green here. So if I plot my points, I got -1 and 2 3/16, which is just a little bit above the red line. And then I've got 0, 2 3/4, which is a little bit higher, but not by much. And then 1, 5, which is about halfway up between 0 and 10. And 2, 14, which is a little bit higher, about here. And 350, suddenly it shoots way up. And if we did 4, it would be like way up here somewhere, way up there somewhere. So you can kind of see this thing starts out down here and then curves up like this. Okay. And again, it's growing. It's exponential growth. All right. Let's see. Let's go on to the next page here. So this is page 4 now. Let's see how we're doing on time. Okay, about 13 minutes in. All right, so in this one we've got y equals, let me make sure I'm recording. Yes, y equals 1/3 to the x. Actually, you know what? Let's skip 5 and do 6. 6 is the better problem. Save a little time. Okay, so let's graph this one. Y equals 1/2 to the x plus 2 minus 4. Well, the parent function is going to be 1/2 to the x. So 1/2 to the x is the parent function. So we'll start with -2, -1, 0, 1, 2. Okay? Well, let's think about what 1/2 to the -2 is. Well, to make that -2 +2, I'm going to have to flip the inside. So it actually becomes 2/1 all squared, which is 4. So 1/2 to the -2 is actually 4. 1/2 to the -1 is the same thing as flipping the inside. So that's going to become 2/1. That is brutal. 2/1 to the first, which is 2. 1/2 to the 0 is just 1, because anything to the 0 is 1. 1/2 to the first is 1/2. And 1/2 to the fourth is 1/4. Sorry, 1/2 squared is 1/4. Okay, well, to get to this chart, I'm going to stretch by 3. Vertical stretch by 3. So this chart's going to be for y equals 3 times 1/2 to the x. So if I stretch by 3, the x's don't change. But the y's get tripled. So now the 4 turns into 12. The 2 turns into 6. The 1 turns into a 3. The half turns into 3 over 2. And the fourth turns into 3 over 4. And then I'm going to shift. So the plus 2 next to the x really means go left 2. And the minus 4 means go down 4. So I'm going to subtract 2 from my x's and subtract 4 from my y's. So if I take away 2 from the x's, I got -4, -2, oh, -3, sorry. -2, -1, and 0. And then if I subtract 4 from the y's, I'm going to get 8, 2, -1, 3/2 minus 4. So that's 1.5 minus 4 is going to be -2.5. And 3/4 minus 4 will be -3 1/4. All right, and then let's do the asymptote. So 1/2 to the x. So 1/2 to the x is going to have really anything to the x, as long as it's just a simple number to the x. It's going to be asymptote of y equals 0. Now, it turns out as x gets bigger and bigger and bigger, these numbers get smaller and smaller and smaller. So it's actually going to be on the right side now. Not that that matters too much, but the 1/2 to the x means this thing's decaying over time because it's less than 1. Okay, the domain is still going to be all real numbers. And the range is going to be everything above 0 still. Okay, so then when I stretch by 3, that just means multiply the y things by 3. So nothing actually changed here. So these guys are all the same. So let me do this. Copy. Paste. Move it right there. Okay. So then I'm going to subtract 2 from the x's and subtract 4 from the y's. Well, if I subtract 4 from the y's, now my asymptote is y equals -4. My domain, I subtracted 2 from the x's. So if I subtract 2 from all numbers, I still get all numbers. And if I subtract 4 from the y's, now my range is going to be everything greater than -4. All right, so let's see what this picture is going to look like. So let's see, we've got a lot of negative x's here. X, y, -1, -2, -3, -4. Up as high as 8, so 1, 2, 3, 4, 5, 6, 7, 8. And down about 4, 1, 2, 3, 4. Our asymptotes at y equals -4. Y equals -4. And let's see here. We've got the point -4, +8. So that's way up here. And then -3, +2. And then -2, -1 would be about here. And then 1, -2.5. 0, -3 1/4. So you can kind of see this thing is decaying this way, like that. Exponential decay. Whoa. I want that right. Okay, there we go. Oh my god. Whatever. Good enough. All right. And then we also did number 7 in class, so after we do that, we'll stop. So if you have y equals a times b to the x, how can you tell if it's growth versus decay? Okay, well, and in this you assume a and b are both positives. If either of them are negatives, you just kind of don't worry about the terms growth and decay. So for growth, we know that that number has to be bigger than 1. And we did that in several problems. That's essentially your growth factor versus your decay factor. Well, if you think about it, you're multiplying, you take some value to start with, and then you multiply by b over and over and over again, however many times x says. So if it's bigger than 1, you keep multiplying by a number bigger than 1, so stuff grows. So if b is greater than 1, then you get exponential growth. Well, if b is between 0 and 1, like a half or a fourth or 2/3, then you take whatever a is and you keep multiplying it by 2/3, and then times another 2/3 and another 2/3, or by 1/4 and another 1/4 and another 1/4. So then you get smaller and smaller and smaller numbers. So if b is between 0 and 1, then you get exponential decay. So you just keep getting smaller and smaller. All right. Hope that helps some, and I'll see you guys later.